hope that this thing starts working. Okay, so let's see if that goes. If it doesn't, I'm going to figure out something else. It was stopping after like 30 seconds. Still okay?
Yeah, still good.
Hi everybody, we're hoping this doesn't shut off. Okay.
Alright, we're good.
It seems to be working. Okay. Hopefully it keeps up. So we want to show that we have a topology. We're taking the real numbers, we're going to take the whole entire space, and then we're going to take all sets that don't have pi in them. Okay? And I want to show that that's a topology. So what's the first thing I need to show? The empty set and the whole space, right? So is the empty set in the topology?
Yes.
Yes, because pi does not belong to the empty set, so this is an element of tau. You don't even need to explain that. Okay, and then is x in the topology?
Yes.
Yes.
Yes, because this is a capital X. Definitely in the topology. Okay, what else do we need to show?
The intersection of two members and tau are in tau.
Finite intersections. Okay, good. So now let U and V be elements of tau. So this just means that, and if either one of U or V is equal to X, then when you do the intersection, you're just going to get either U or V, which is already in tau. So assume,
Bless you.
thank you. Assume U and V are both not equal to X. Because if they are, then the intersection is just trivial. So what we want to show is that U intersect V is in tau. Well, that would mean that pi should not be in the intersection. So do we have that?
Yes.
Absolutely, because U and V are not equal to X, then they have to be over here somewhere, right? Okay, so pi is not in U, and pi is not in V. Okay, thus, pi is not in the intersection, so U intersect V is in tau. Okay, very good. Okay, so what else do we have to show?
Arbitrary
Infinite
union.
union.
Yeah, right.
Arbitrary unions, exactly. So finally, let's let the set of U sub I, where I is in some index set, let's let that set be a family of sets in tau. Okay, and what again, if any one of those sets is all of X, then the union of all of them would be
Just be
X, which is in the topology. Okay, so we may as well assume that these sets are not equal to X. So we can assume U sub I does not equal X for each I, and therefore it's one of these, right? So this just means that the key factor that puts something inside of here is that pi is not in any one of those sets, right? So for each I, pi is outside of U sub I. Okay, and so therefore, if we take the union of all of those, right, will pi be in there?
No.
No, because it's not in any of the sets, right? So this excludes pi. So the union of the U sub i's is in tau. So it's closed under unions. This make sense so far? Awesome. So it's a topology. Okay, so we have a good topology now. So now here's my next question.
I have a quick question.
Yes.
But we said let tau is equal to the whole set union parts of its set.
tau actually tau does not equal x union these sets. It equals the set of x
Okay.
union with these sets over here. So remember, a topology is a set of sets. So this is just actually a single member of the set tau.
Right, but if we have the whole set of x, we have the whole set of real numbers union with any part of the real number.
No. You're taking the elements within the set and you're unioning
okay.
them with the other set. There's a difference between x and the set of x. This of course is the whole real numbers, and sure, if you take the union of that with any other part of the real numbers, you're just going to get the whole real numbers. But I'm making a bunch of sets and just throwing them into a larger set. This topology is like, it has a big curly braces around it, and maybe we could just say it this way. It's like that.
Okay.
There's this set, actually, and now I can take this off of here, sorry. It's like that. So tau has that set in it, and it has any one of these kind of sets in it.
Okay.
Okay. Great. So here's my next question. I want to get on to the fun part here. Is tau T0, T1, T2, T3, T4, regular, and or normal? And circle all that apply. On the take-home test, I asked you guys if a set was, a lot of you said that something was dense, but then I said, is it dense, somewhere dense, or nowhere dense? And a lot of people said, oh, it's dense. But well, if it's dense, you should have also said that it was somewhere dense, because the dense set is always somewhere dense. I didn't take off points for that, but technically you should circle everything that applies. So I hope everybody remembers the relationships here. Remember, T0 is the weakest property, right? T1 implies T0, T2 implies T1, T3 implies T3 together with T1, which is regular, implies T2, and T4 together with T1 is normal, and that implies T3. So make sure you know the relationships here, okay? So, question is this topology, which of these axioms is it going to have? So my advice would be to start at one end or the other. If you check normal and it's normal, then it's going to be everything. If you check T0 and it's not T0, then it's going to be none of these. The problem is if you start in the middle somewhere, you say, well, I'm going to find out if it's Hausdorff first. Well, that's fine. If it's Hausdorff, then you'll know all this side, but you still have to check these. And if it's not Hausdorff, then you'll know that none of these work, but it might be one of these. You see, so it's better to, I think, start at the ends of this list if you get a question like this. Either start by thinking about T0 or start by thinking about normal. So I'll let you guys think about it for a minute. You have to remember the definitions, and if you don't know the definitions of any of these 7 things right here, you definitely need to get the flashcards going, put them under your pillow for the next 2 nights, and soak it up, because it's going to be on the test. I can tell you right now. The separation axioms are going to be there. Jason?
Because the closed sets must contain pi, we wouldn't necessarily have disjoint closed sets, correct?
The closed sets must, so the closed sets, actually that's a good question. What are the closed sets here? Let's look at that. The empty set is a closed set that doesn't have pi in it.
Oh, correct.
But you're right. So the closed sets, remember, are just the complements of the open ones. So just for our reference, this might be useful for us. The closed sets are the empty set, which is the complement of X, and then the complement of any one of these things. Well, what are these sets? These are just subsets of the real numbers that don't have pi in them. So if you take the complement of that, well, you'll get sets that do have pi in them, right? So this is just going to be all subsets containing pi. So together with the empty set, it would just be all sets, subsets of R that do contain pi. Agreed?
And then hex itself.
And then, well, that would include
Oh, yeah.
this, yeah. Exactly. Okay, so let's just see. So what does T0 mean again? It means, by definition,
Yep.
any two distinct points, there exists an open set that contains one of them but not the other. Okay, so would that be true here? For any two distinct real numbers, can I always find an open set that contains one of them but not the other? So, you know, you might have to play with it for a minute. Think about like what could happen. Well, you could use, and because pi is, you know, a big part of this definition of tau, you might want to think of one of the sets being pi and then pick a different number. Right? So if I, just as an example, if I chose these 2 points, can I find an open set that contains one of these but not the other?
Yeah.
And we're talking about these open sets up here, right? Namely, what open set would you pick?
U3.
The set of 3. That is your open set. This is open because pi is not in it. It's an open set that contains that, but not that. Okay? So that works. Now, what if neither of the, what if this is a 4 instead?
That still works.
Still works, right? Still works. Given these 2 points, is there an open set that contains one of those points but not the other? Sure, you can use the same set U. Okay, so it is T0. It is T0. Okay. So now, at this point, we can either go to the other end and ask ourselves if this is going to be, you know, normal, or we can look at T1 next. You know, so now T1 is just, the definition is just that given any 2 points, there's an open set that contains the first one but not the second, and an open set that contains the second one but not the first. Do you think that's going to work?
No.
So why not, Alice?
Because singletons are not close.
So give me, oh, so you just want to use the characterization. That's a great proposition to remember, guys. In a T1 space, singletons have to be closed. So can you give me a singleton that's not closed?
3.
Okay, this set is not closed because the complement of it, which is everything except 3, is not open. The complement would have pi in it, right?
Yeah.
Yes.
So the complement of this is not open, so therefore this set is not closed, so it's not T1. Alternatively, you could just use the definition and say, look, here's 2 distinct points. You cannot find an open set that contains this one, but not this one. Because the only open set that contains pi is the whole X, right? Which also, of course, contains 3. Right. So the way I define this topology, this is not T1. So if it's not T1, then none of these others are going to work. Right? It's only T0.
Really? What about T3?
Because T3 doesn't imply T2, which doesn't imply
Right.
T1.
Okay. So
Would T3 work?
that's a good question. I need to back. I need to. So okay. Sorry, I went too fast. Get too excited here. Let's back up for a second. So T3 and T4 both we should leave. Definitely not regular and normal because regular is T3 plus T1, and we know T1 is not true. So so this implies not T1. Okay, so let's remember the definition of T3. I'm going to actually write it down here. It just says anytime you take a closed set inside of X, and then you take a point that's outside of that closed set, then there exist open sets U and V with F inside of U. Actually, I think I used X in the definition of this. X is inside of U. I mean, this is probably not going to work, is my guess. I just need to stop and think about it for a minute. And U intersect V is empty. So, so let's think about this. A closed set, we have to take a closed set. Here's what my closed sets are. And I really can't use this closed set because there's no X outside of it, right? There's nothing outside of it, of this thing because it's just the empty set. So, well, actually, so hold on. No, I can use this and just pick any X outside of that. I'm sorry. So I could choose the empty set and then just pick a number. So if F is the empty set, then I can choose V to be the empty set as well.
Yes.
Right? And then I just have my point that's not, well, I can pick any point, right? And I just have to put it inside of an open set. Well, I can do that. I can just put it inside of, except for, well, even for pi. Even for pi I could do that. If X is equal to pi, then my U would have to be the whole X, because that's going to be the only open set that would contain it. But that's okay, even if U is equal to the whole X, because V is empty, the intersection will be empty. So, okay, so it kind of trivially seems to be T3.
Oh, what about all the, what if you choose F to be all subsets of R containing pi?
Oh, okay, so we took this, we took the first one, and we saw that works. So now suppose we take a subset of R that contains pi.
That's not true.
So you don't think it's going to work now?
Because F contains pi.
Yep, I think you're right. I think this is not going to work. So if we take, let's actually take a specific example of a counterexample here. So let's take a closed set. Let's take, well, we could just take that closed set. Okay? Everybody agree? That's a closed set? Anything that contains pi is closed. So there you go, there's a closed set. Pick an X that's outside of that. I'll pick 3. Okay. Question is, can we find open sets that contain these two things? Well, the only open set that will contain pi is going to be X. So that means that I have to choose V equal to X, right? And I need an open set here that 3 belongs to. Well, there's lots of them, but unfortunately, they're all non-empty because they have to have 3 in them. So 3 will have to be an element of U. Whatever the U is has to contain 3. And now look at the intersection of U and V. It's not empty. Okay, so this is a no, actually. Change my mind again. Okay.
But it is T4, isn't it? Since the only disjoint closed sets for that are the empty set and some other one of those sets? Like if you have 2 closed sets that are disjoint, one of them has to be the empty set.
2 closed sets that are disjoint because the closed sets of the empty set and all subsets that contain pi. So if you had 2 closed sets that were non-empty, they would both have pi in them. That's what you're saying.
Right.
Right.
So one of the closed sets, this is